get ready to go on a roller coaster that will...
Hi everyone. I welcome you to the next chapter that we have, which is acids bases from the autonomous syllabus for the grade 10th. And we will be looking at today all the details of how really to write your answers for your upcoming boards. We have already seen one chapter. This is the second in the series that we are bringing up for the autonomous syllabus. With the title of acids and bases. Now, let's understand to begin with what's acids and bases. This is quite a lengthy chapter, and so we'll try and see as many problems as well as the variety of questions that we can really look at. If you are listening to this, I would recommend that you actually send us a quick chat note on the video chat. You can always mention your queries below at the chat, and I will be able to answer them. You can also message me or text me in the WhatsApp, and I'll try and bring that up while we are answering the questions. So let's begin. I'm going to make have a quite small pause so that there are a few who are still joining in, and I hope that they come on board before we really get into the problems or the theory. Yes, so all those who are present, can you please put your name and I'll be happy to have a look at those. Okay. Yeah, so let's begin. Let's understand what are acids and bases. Yes. Yeah. So let's understand what is acids and bases. Now, so Sai is here. Sai, this is for the autonomous syllabus, but you're most welcome to hear it. So long that you find time for the same. We are waiting for all the other autonomous syllabus students to join in. Right. So let's begin. Given the paucity of time that we have, we will have to cover a lot. We are going to look at a lot of slides today and understand how this really can be dealt with for the upcoming boards. So a quick look at what are acids and bases. The first thing that acids and bases are different compounds that are having properties. So Aditya is here. That's nice. So acids generally are sour in taste. Bases are bitter in taste. In fact, the very word acid comes from asar, ACAR, which means being sour in taste. Of course, all the acids turn litmus papers to bases turns litmus paper to blue. It can be remembered as BRB, blue turns red to blue. So BRB is a short form to remember that blue turns litmus to red to blue. And yeah, that's how. And if you remember the bases, so bases turn red to blue. If you are able to remember that, automatically your acid can be really worked with. That's nice. Ronak is here. Aditi is here. Nice to see you guys. We'll continue further. Of course, acids neutralize alkalis and bases neutralize acids. Any of you who have joined in, if you have any doubts at any point of time, please feel free to put in a text on the YouTube chats, or you can always message me on the WhatsApp as well, and I'll be happy to answer your queries. Now, right. So now let's move forward. There will be a few reactions that we'll see of acids and bases that are important to your syllabus. So for example, all metals give hydrogens and it gives CO2. Metals give hydrogens when it reacts. Acids react with metals. When acids actually react with bicarbonates or carbonates, we end up getting CO2. So for example, H2CO3 decomposes into H2O plus CO2. Whereas bases actually end up giving a soapy touch. Some common acids that we know of very well is HCl, H2SO4, nitric acid, acetic acid, whereas bases are sodium hydroxide, potassium hydroxide, calcium, and ammonium hydroxide. Some common acids that are found around the house. The acid that's there in our stomach is actually hydrochloric acid, of course, to a quite a dilute extent. H2SO4 is pretty much used in the car batteries, especially with lead. Nitric acid is something that's used in explosives. For example, TNT is made from nitric acid, trinitrotoluene. Then acetic acid, which is nothing but CH3COOH. So Mansi has just joined. Good to see you, Mansi. Yes, so then acetic acid is used in vinegar. Similarly, there's carbonic acid in sodas. All the aerated drinks that we have is basically carbonic acids. Of course, and phosphoric acid is used in flavorings. In whenever we use any food, etc., we have flavors in it. I can see Momika as well. That's nice to see you all. Let's go further. So we've just started with acids and bases, and we have seen what acids and bases really are. Another few common acids that you should know about is citric acid in orange, citric acid in lemon. In tamarind, we have tartaric acid. Anirudh is here. Hi, Anirudh. Then we have oxalic acid in tomato, in lactic acid in milk. Actually, sour milk, when it turns to curd, milk mostly has lactose. And when it converts to lactic acid, that's when curdling happens. Whereas whenever you have an ant or a nettle sting, it's formic acid that really burns your skin. So these are a few common acids that we know of, and then there are some common bases. For example, NaOH, which is used in soaps and drain cleaners. We also have magnesium hydroxide, which are used as antacids. So whenever you have acid reflux, for example, when you have indigestions or a lot of acidity in the stomach, which we commonly call it, which technically is called as acid reflux. I can see Neha has also joined in. Then it's that's nice. Okay, then we actually use magnesium hydroxides. We also have aluminum hydroxide, quite commonly used in deodorants, and then ammonium hydroxide, which is a very weak acid as ammonia. So that's a quick look at what acids and bases are, and some of the important reactions of acids and bases is when acid reacts with metal, they end up giving hydrogen and salt. A test for this is you can actually use what we call as a pop test. Whatever hydrogen is released, you can just use a small a splinter or a small fire, which can actually bring about a pop sound, which is because hydrogen burns quite explosively with fire, with oxygen. So that's where this pop test is very useful when you're testing whether something is an acid or not. You simply put a metal in it, and you will find hydrogen being given out. Now, similarly, if you look at bases, some bases, not all, for example, zinc and aluminium for sure. I've just mentioned zinc here, but just for your information, even aluminium does the same. So aluminium and zinc both end up giving these, the hydrogen gas out. When zinc forms sodium zincate, aluminium forms aluminium zincate in the same process. So this is a quick test for even bases, especially the strong bases. Please note that these reactions are not possible with all metals, as I've already mentioned to you. So that's acids and bases as an introduction. Now, we've also seen one more reaction with carbonates and bicarbonates. So if you really see, if there is a metal carbonate and acid, you'll realize that CO2 is given out. For example, Na2CO3, which is nothing but washing soda. If you put small drops of HCl in washing soda, rigorous effervescence of CO2 is seen. Similarly, sodium bicarbonate, which is NaHCO3, also called as baking soda commonly, you put small drops of HCl in it and CO2 is given out. So these two reactions actually signify the properties of acids. And then you have a litmus test through which you can actually understand how to really recognize CO2 that is coming out of the solution. The lime water test essentially is CO2 is passed through calcium hydroxide water, which is nothing but lime water, and this actually turns the calcium hydroxide into a white precipitate or milky because of the formation of CaCO3. But if you pass the CO2 for a very long time, CaCO3 dissolves because of the formation of calcium bicarbonate. So whatever was white with CaCO3, you'll realize the same becomes CaHCO3, and it's soluble in the solution. So white becomes colorless if you pass more of CO2. This establishes the presence of CO2 in acids and bases, in the reaction of acids and bases. Another reaction very important for acids and bases is, of course, neutralization reaction. So NaOH and HCl, which is nothing but a base and an acid reacting together, will end up giving NaCl, which is a salt, plus H2O, which is water. So this is a typical neutralization reaction that we have. Then there is reaction of metal oxides with acids. Remember this one very important trick, or maybe a short form. All metals, all metal oxides, so that is MO, and all metal hydroxides, all of these three are always basic in nature. They never are acidic. Sometimes they turn to being amphoteric. That means that they are basic and acidic at the same time, but never acidic. So amphoteric ones are rare. For example, ZnO, Al2O3, these are all amphoteric oxides. But in all other cases, in most of the cases, all metals, all metal oxides, and all metal hydroxides are generally basic in nature. So as you can see here, CuO with HCl is works as if it's forming a salt and water. So we can realize that the CuO is actually working like a base with an acid. So that shows its basic quality. The blue color that is formed, of the solution is because of CuCl2 that is precipitated out or is formed in the process. So all metal oxides generally are said as basic, as we have said, because they give out salt and water in the process. Now, when we have non-metallic oxides, on the other hand, we end up getting a very acidic reaction from them. So, for example, we have non-metallic oxide CO2 in our reaction that's there on the screen. This reacts with a base, which is COOH twice, to give out a salt and water. So non-metallic oxides are said to be acidic in nature because they react with a base to form salt and water. Again, just to really remember the trick, all non-metals, non-metal oxides, I can write it as NO, and non-metal hydroxides are basically acidic in nature, and they would react with any base to end up giving, so if there is a base, to end up giving a salt and water. So this is a quick look at what acids bases are. I thought we would touch base upon some properties of acids and bases before we get into important topics like how to really look at their strengths and what are their definitions. So once we've understood what acids and bases are, now let's understand how we really defined acids and bases in the first place. Who were the guys who gave the properties of acids and bases, and how do we really understand them as seen today? So you'll realize that acids and bases were given, these definitions were given by three people, ARRHENIUS, BRONSTED, LOWRY, and LOWRY. So if you look at ARRHENIUS definition, it is almost more than about 200-year-old, 140, 150-year-old now, and you realize that those were one of the earliest experiments that were being done. After which BRONSTED, LOWRY, and LOWRY, both of them having similar tenure around 1920s, gave two more definitions which are more commonly accepted now. So let's look at what were their definitions and why was there a need to revise the definitions over time. The first definition was given by ARRHENIUS, and he very simply said that anything that you put in water, this is a very important term to understand. ARRHENIUS gave definitions only for aqueous solutions. He did not have much to say when substances were not dissolved. So in aqueous solutions, he simply meant that whenever H plus is given out, that's an acid, whereas whenever OH minus is given out, that's a base. In fact, going forward, he also did mention that some substances actually give a lot of H plus and some substances give a lot of OH minus. So from his time, there were known that the activity of H plus and OH minus are different for different substances. But he had limited his definition only to defining them around H plus and OH minus as such. So hydroxides were considered to be bases in ARRHENIUS time, whereas hydrogen compounds were considered to be acids. One very important thing we have to remember here is H plus being simply a proton, it is very unique ion. Yeah, in fact, if I have to say, it is a cation, so very unique cation. Firstly, because it is very similar to a proton and there is no electron around it, the nucleus size is also equal to the size of the proton itself in an H plus cation, or simply a hydrogen ion. Now you'll realize that since the nucleus is equal to a proton size, it's very, very small in size, and therefore it is extremely reactive. So most of the times we actually do not consider H plus in its H plus form, but we actually consider an attraction between H plus and water to talk in terms of an hydronium ion. And hydronium ion is nothing but an H3O plus, which is an H2O plus and hydrogen ion, which is a proton. So this small proton that you can see here, I've just relatively tried to put up a size. So it's so tiny. It actually is in presence of a huge atom, that is oxygen, which has almost it has 8 electrons and also has 2 lone pairs, which are very strongly attracting this proton. So all it has to do is connect to these lone pair and have a third bond. So that's how an hydronium ion is placed, and most of our definitions forward, you will find that instead of H plus, we actually keep on talking about hydronium ion presence. So that's the Arrhenius definition and hydronium ion as such. But you see, not everyone was happy about Arrhenius definition. One of the major problems with Arrhenius definition was that it was limited to being only for aqueous solutions. Now, we had seen salt formations even in gaseous form. In solid form, definitely there was a presence of acid-base reactions. So there was a question as to whether Arrhenius definition was sufficient or not. Also, since acid requires water to ionize and form hydronium ions, there can be no Arrhenius acids when water was not involved. So we needed a definition beyond water as a solvent, and therefore new definitions were produced. One of the first guys to give the new definition was BRONSTED, LOWRY, and their definition was very similar to Arrhenius, but with a slight change. They said, we agree that acids give out H plus, but we don't need water anymore. So anytime whenever someone is giving or donating an H plus, that's actually acid. But at the same time, they slightly changed the definition of OH minus, because if you also realize, giving OH minus in the gaseous form is something that's technically difficult, as well as not very stable. A proton donation even in the gaseous form is an easy one, because proton, being a very small tiny ion, can actually also stay in the gaseous form. But that's where they changed the definition of base, and they said it's not OH minus donation, but it's H plus acceptance. So if you really look at anyone who is an OH minus donor, would also be taking out H plus to form water. So the definition actually fit in the reactions pretty well, and they were able to define all the reactions that were shown with an OH minus donation, also with an H plus acceptance. And therefore, BRONSTED, LOWRY defined an acid as proton donors and base as a proton acceptor. One example that I've shown here is HF with water actually forming an hydronium ion and an F minus ion, which is nothing but an anion. So that's acid base according to BRONSTED, LOWRY theory. Now, because of the BRONSTED, LOWRY theory, a new concept of conjugate acid base became pretty prevalent pretty soon. So you realize that the conjugate acid was formed just by an exchange of a proton from its counterpart, which is the base. And similarly, base was formed from an exchange of proton from its counterpart, acid. So a common reaction sometimes looks like this, is where you have HA, which is actually reacting with water to give out an H3O plus. So the acid actually turns out to give a base. So this acid-base pair is actually a conjugate acid-base pair. We'll quickly see in the new in the next slides as well. And here also you'll find that the difference between conjugate acid base is just an H plus ion. So let's look at a few more reactions of acid-base pairs. You'll realize that when ammonia is put in water, most of the ammonia actually dissolves, and we will find that NH3, when it is dissolved form, will be in the NH4 plus form, which is nothing but an ammonium ion. Whereas the OH minus will be remaining because it was taken off, one of the hydrogens was taken off from the water, and therefore you will find that OH minus is present. So to figure out an conjugate acid-base pairs, always look at how H plus is moving from reactant to the product. And so in this scenario, you'll find that the H plus from H2O has moved to NH3. So it has jumped from H2O to NH3. And sometimes it's also called as the bouncing proton or bouncing H plus. Now, when H plus has moved from NH3 to from H2O to NH3, whatever is left behind is OH minus. So if you really see the base 1 and acid 2, if you really go forward and look at them, the base 1 has an acid 2 has created the base 2, and this is the acid 1. So it's pretty easy in this scenario to really figure out how acids and bases have worked up. And if you compare them, you'll find that the base 1 has created acid 1 and the acid 2 has created base 2. And in both of them, there is a difference of a single H plus. So here there is an H plus that is added more to NH3, and here there is an H minus that has been taken out of water as you go towards the right hand side. So this is an conjugate acid base pair. This is how you can actually understand and relate to conjugate acid pairs. I can see that Arpita and Ananya has joined. Nice to see you guys. Yeah. So we have just finished the introduction of acids, bases, and we have looked at their reactions. Now we are looking at the definitions of acids, bases. We have already seen ARRHENIUS definition, and we are looking at the Bronsted-Lowry definition, which is where the concept of acid-base conjugate pairs is very important. Generally, it's said that whatever is on the product side is the conjugate of the one that is on the reactant side. So NH4 plus is the conjugate of base. A very common mistake that people end up doing here is to figure out the conjugate acid-base pairs is the base and base are related. I don't know how we can go wrong here, but some of the solutions that I found from students is the NH3 is related to OH, but that's not true. The base has to be related with the acid. And how do we know that this is an acid? Because if you go in the reverse direction, NH4 plus is the one who is going to give H plus, which means that it is acting like an acid. So what are the tricks? Just to summarize how to really identify conjugate acid-base pair, anyone who is giving H plus is going to be an acid. Anyone who is taking H plus is going to be a base. Once you have given H plus and you have gone to the other side, look on the other side who is going to accept the H plus. That is going to be your conjugate base. Let me give you an example. In this scenario, H2O has given H plus and it has formed OH minus. Now on the other side, since H2O has formed OH minus, it is the H plus that is taken by NH4. So while you move from H2O to OH minus, you will find that this acid is created. NH4 plus is created. Why? Because when you create the backward reaction, it is the NH4 plus which will be giving H plus to OH minus, right? So that's a quick look at all of these acid-base pairs, conjugate pairs. Good. Now let's look at how we really see in a few more examples. So here we have actually acetic acid, but I have written it in the form where H plus can be seen with the acetic acid separately. So you'll realize that the acetic acid gives H plus, so therefore it's definitely an acid. And as it gives H plus, water takes up that H plus. Now, if you go towards backward reaction, it will be the water who is going to give H plus to the acetic acid. And therefore, you'll find that it's the hydronium ion that is going to act like an acid. So that's how we can figure out the conjugate acid-base pairs. You can also write them in a form where you can write acid plus base gives conjugate acid plus conjugate base. Now let's figure out how H plus has moved in this. Once again, as I've said, from acetic acid, H plus has moved to the water, and in the reverse reaction, from the water, the H plus has moved to the acetic acid. Now, if we have to understand the relative strengths of acids and bases, we have to understand the stabilities of their conjugates. Now, here's a formula that I could come up with. So whenever an acid is very strong, its conjugate base is going to be very weak. When the acid is going to be strong, conjugate base is weak. So they are inversely proportional. When the acid is weak, the conjugate bases are strong, so on and so forth. And let's understand why is this why is this kind of a scenario present. It's because you'll see when you have an acid like an HA, and let me probably use a thicker line. So when you have an acid like HA and it gives out an A minus, let's say if A minus is very stable, if A minus is very stable, it means that it is going to be a very weak acceptor of H. So if it is stable by itself, it will not have H getting accepted in the reverse process. So if HA is going to A minus and A minus is very stable, then HA would also want to be on the A minus side of the equilibrium, and hence it would be a very strong acid. So HA is a very strong acid and A minus is a very stable conjugate base. and therefore, because it is stable, it will also be a weak base. So that's a quick way to really understand how acid and bases can react with each other. Now coming back to our formula of acids and bases. When acids are very strong, conjugate bases will be very weak, and so on and so forth. So remember the inverse proportion of acids and their conjugates, and that is also true with bases for that matter. When you have bases and conjugates, if the base is very strong, its conjugate is going to be very weak. uh, at some point of time, if you ever feel that one of these concepts is something that you could not relate with, the good part of doing it on the YouTube is that you can always pause this, you can rewind, maybe after the class you can come back and have a look at it and get your concept verified. So that's a quick way to look at acids and its conjugates. Now please note, when strong acid lose proton very easily, obviously weak conjugate bases will be formed. This is just what we really saw in a quick minute. Now, sometimes it also happens that the acids are going to give H plus, but at the same time they are also going to take H plus, and such acids or bases are called as amphoteric. So let me give an example. Let's say I have an H2A. The H2A, let's say in the first instance, it gives out HA minus plus H plus. Now, since it has given H plus, this is an acidic behavior that it has shown. So definitely H2A is an acid. But please look at HA minus. When you have HA minus, in one form, it can take H plus to form H2A. So this is a basic behavior that HA is showing. But at the same time, HA can also give out another H plus. When I write minus H plus, it's giving out H plus to form A minus plus H plus. Now, in this scenario, this is actually showing a very acidic behavior. So you can see at the same point of time, both HA minus and HA are showing basic as well as acidic behavior, and hence such substances are called as amphoteric substances. So what are amphoteric substances? Amphoteric substances are those which actually can show basic and acidic behavior at the same point of time. Now, let's look at some amphoteric substances in H2O. For example, we are using the definitions of Bronsted, LOWRY here to find out which are the conjugates of it. So conjugates are basically the counterparts of the acids or the bases that are formed after exchange of an H plus. Like in the previous example, we had HA minus as the counterpart of H2A. So that's the relationship between a conjugate and an acid or a base. Now let's look at the H2SO4 molecule. So if you see, they are always strong acids in water. They are not amphoteric because H2SO4 can only give out H plus. So definitely H2SO4 is not amphoteric. Let me also ask you guys, and you can actually answer this. You can answer on the chat as well. What do you think? Is HSO4 minus an amphoteric acid or base, or an amphoteric substance rather? Is HSO4 minus an amphoteric substance? You can actually mention the answer in the chats as well. You can give it for SO4 minus as well. Also in the previous gaps that I have mentioned, you can mention what would be its conjugate base or conjugate acids equally. So all those who are up on the live right now, you can please put in all the blanks. I have mentioned all these blanks here. Let's see how many of you really get this one. Okay, so I've received an answer here which says yes, HSO4 minus is amphoteric. Yeah, let me see for a few more. So Ruhi says yes, it is amphoteric, and okay, SO4 minus is always basic. Let's see what it really is. So yes, HSO4 minus definitely is an amphoteric because it ends up giving H plus as well as it ends up taking H plus. Correct, that's right. Momika as well says that it's amphoteric. What do you think about SO4 2 minus? Others, if you are unable to type in, you can always put it down on your notebook and check your answers later on. Right, and SO4 2 minus is actually always basic, right? Because it will only be taking up H plus. It cannot really give out any H plus. So HSO4 minus can give out H plus to form SO4 2 minus, and therefore it is acidic in nature. but at the same time, it can take in H plus to form from H2SO4. So it is also basic in nature, and hence HSO4 minus is amphoteric substance. Now, if you look at the other conjugate acid base pairs, F minus is the conjugate base of HF, whereas HSO4 minus is the conjugate base acid of SO4 minus. Now, please note, whenever you're going from, this is another trick, sometimes it is very confusing. So if someone asks us what is the conjugate acid of this, then we have to understand that the acid is going to give H plus. So while I found the conjugate acid, I will have to take in one SO4, so SO4 minus from it. So when HSO4, H2SO4 will give out an H plus to form HSO4 minus. This is the conjugate acid of HSO4 minus. So if you see the next answer, HSO4 minus will actually end up forming H2SO4 when you're talking about conjugate acid of it. But if you talk the conjugate base of HSO4 minus, it will be SO4 2 minus. So so the idea is that the difference of H plus where you have to end up is something that you'll always have to think about. Now, if you look at NH4 plus, which is ammonium ion, its conjugate base is ammonia. Similarly, when you look at H2O and OH minus, you'll find that the conjugate base of H2O is OH minus, and the conjugate acid of H2O is actually H3O plus. What I would recommend to all of you is, after you've gone through all of this slides, you can always wait and rewind and actually try these sums to find who are the conjugate acids and bases as such. Now, let's look at what is the relationship between Arrhenius and Bronsted-Lowry. So in Arrhenius definition, we had said they are H plus donors, acids are H plus donors, whereas bases are OH minus donors, but and they only exist in water solutions. But if you really look at Bronsted-Lowry, Bronsted-Lowry is a much larger definition, and therefore all Arrhenius acids bases are definitely Bronsted-Lowry acids bases, but the other is not true. The other way is not true. So you'll find that all Bronsted-Lowry are not actually Arrhenius acid bases. So Arrhenius acid bases can exist when even water is not present, and therefore it is a larger circle. So this is the relationship between the definitions of acids bases with Bronsted-Lowry. Now, the last definition that was given out was basically by Louis, and it's pronounced as Louis, although the spelling is Lewis. He said that, okay, this all looks good, but sometimes there is no hydrogen, and still we are able to see that there is a salt reaction that is possible. A classic example is AlCl3. So you can see that AlCl3 actually reacts with, for example, HCl to form something of sort AlCl4 minus plus H plus. So HCl is an acid, but AlCl3 actually takes in the chlorine Cl minus to form AlCl4 plus H plus. In the reverse reaction, it is the H plus that is taken, and therefore this reacts like a base, and AlCl3 here acts like a base here as well. But just look at how the reaction proceeds. I can write this entire reaction in one word form. I can say this as AlCl3 is actually taking Cl minus to form AlCl4 minus. Okay. Now, to accommodate all of these reactions, you will find that Lewis actually gave a new definition, and he said acids are basically pair of electrons, are the ones who actually accepts pair of electrons, whereas bases are those who actually donate the pair of electrons. And this is a very general definition, more general than Bronsted-Lowry. A common example I've also mentioned here is the ammonia. So you'll find that ammonia gives its pair of electrons with H plus to form NH4 plus, which is an ammonium ion. So there are three definitions that we have seen so far. One is the Arrhenius, second is Bronsted-Lowry, and the third is Lewis. The definition of acid is H plus producers and OH minus producers of acids and bases respectively. Bronsted-Lowry is H plus donor and H plus acceptor. So please remember the use of word producer and donor. Producers is basically we have used because they are in aqueous solution, and donors we have used because they are also possible in the gaseous solution. And then it's the Lewis definition which we have, which is electron pair acceptor and electron pair donor. Now, we have just understood what acids and bases are, but we have not really looked at the strengths except for looking at its conjugates. But if you really have to measure the strength of an acid and base, we will have to define something called as a K and Kb. This concept actually comes from equilibrium, where the reactions of acids and bases are written in terms of an equilibrium being established between the products and the reactants. So let's take an example of a weak acid, which is CH3COOH. You'll realize that CH3COH in water gives out an hydronium ion plus CH3CO minus. We all know this. But since this is a reversible reaction, please note the symbol that I've mentioned. Although it's like looks like resonance, it's actually the symbol of reversible reactions or reactions which is in equilibrium. The K for this reaction can be defined as, if you remember in equilibrium, we always wrote K as products divided by reactants. Products divided by reactants. Okay, so you'll find that we have mentioned the products here, which is H3O plus and CH3CO minus. Both of them is mentioned, and CH3COH and H2O is not mentioned here. Please note, we are going to look at that in a few minutes, but why is it not mentioned? But this is basically an equilibrium reaction. Because the equilibrium is for dissociation of acids, we call this as Ka, or commonly it is called as the acid constant or the dissociation constant for a weak acid. Similarly, for a base where we have NH3 plus H2O, we have written the products divided by the reactant. Again, here we have, please note that we have not written H2O. We'll see in a quick minute why H2O is not written. But this definition is called as the equilibrium constant for a base. So acid and base ionization constants are the measures through which we can understand whether it is a very strong acid or a weak acid, so on and so forth. So obviously, whenever the value of K and Kb is very large, you will find that the strength of the acid is also higher. Why? Because if this equilibrium is going to be on the right hand side for a lot, CH3CO minus concentrations will be very large, and similarly in ammonia, if it is on the product side, again the concentrations of NH4 plus will be large, and therefore the value of Kb and Ka is going to increase. So larger the value of Ka and Kb, stronger will be the acid or base. That's a quick thumb rule through which you can understand the strengths of acids and bases. For your reference, I have given you some values, and you can really see how acid and base values really change. So you see this is 1.1 into 10 to the power minus 2, and this is 6.2 into 10 to the power minus 10. So you'll see that the Ka values have sharply increased as we go up. So this is a very high Ka value, and you'll therefore find that the chlorous acid, which is HClO2, is a very strong acid. In fact, it is stronger than HF and nitrous acid as well. If we look at some carboxylic acids here, again, I have just given you a list so that you can really see how strong or weak something is. So acetic acid is a very weak acid. You can imagine it is at 10 to the power minus 5. In fact, chloroacetic acid, I have just replaced one hydrogen with chlorine, and its acidity has increased almost 100 times. Not 100, in fact, yeah, that's right, 100 times. So you'll see that from CH3 to chloroacetic acid, by just replacing a chlorine, you'll find that the acidity sharply increases. So the H plus giving ability is very large for this. Now, and similarly, I've given you some more values. You can always, again, come back and look at these values to get a very good idea as to how Ka value relates to the strength of acids and bases. Now, just extending the same argument, weak acids, ionize to a very small extent, and therefore their Ka values are very, very low. And they come to a state of chemical equilibrium absolutely at very small dissociations. Now, depending on how much it ionizes, equilibrium constant is calculated, and as we mentioned, larger the Ka value, stronger the acid. And so does it will give out more ions in the solution or easily donate a proton. Right, we have also seen this. Now let's look at why we had ignored H2O. Now the idea of ignoring H2O in the reactant side while we wrote the equilibrium is because H2O is actually a it's in the liquid form. So if you really look at its concentration basically is given as moles per liter. Now, we know that 1 liter of H2O is approximately equal to 1000 grams, because the density of water is 1 gram per cc, and 1 liter is actually equal to 1000 cc, and therefore it will be equal to almost 1000 grams. But 1000 grams, we know that 1 mole of water is also equal to 18 grams. So 1000 grams is nothing but almost 1000 grams is actually equal to 55.5 moles, uh, sorry, 55.5 moles of water. So it essentially, what I'm trying to show in here is that the concentration of H2O, if I have to really mention, is as high as 55.5 moles per liter. That's the concentration of water, pure water. Now, if you are going to take this concentration at the bottom, and we know that HCS3CO minus, these values are in the powers of 10 to the power minus 3 or 10 to the power minus 5, you'll realize that taking a very large value actually makes no difference. So the this 55.5 is going to change to only 55.5 minus 10 to the power minus 3, which is basically a insignificant change. So since the H2O is not changing at all, we do not consider writing H2O at the base in the reactions, and we completely omit that. Therefore, the water is not written when we actually look at the equilibrium reactions of acids. Now, let's understand what happens with water particularly. We have seen that everything gives H plus, OH minus. We have seen all the three definitions. Water is unique because it gives H plus, OH minus both. At the same time, the neutralization itself is defined with respect to water. So what is water defined with respect to? So if I have to define the activities of water, how will we do that? So ionic product of water is something that addresses this query. In ionic product, you will find that we basically have an ion product of H plus and OH minus taken. Generally, it's taken at a particular temperature. The common value is taken at 25 degrees Celsius, which is nothing but our room temperature, or 298 Kelvin. So you'll realize that the ionic product of water is written, if you look at this equilibrium where water dissociates, it can be written as H plus into OH minus divided by H2O square. But again, please note that H2O square is going to remain constant forever, and therefore we can just simply omit that. And therefore, the ionic product can simply be written as H plus into OH minus. Instead of H plus, we are writing this as hydronium ion, and we are also fixing the temperature, which is at 25 degrees Celsius. Definitely, when both H plus and OH minus are in equal proportion, we call that solution as neutral. But please note, as soon as they become equal in proportion, you'll find that, one quick second, when both of them are equal, it's basically H plus square is equal to 10 to the power minus 14, and therefore automatically H plus is equal to OH minus, and it turns out to be 10 to the power minus 7. So you'll realize that the ionic product of water is 10 to the power minus 14. This results the concentration of H plus and OH minus to be 10 to the power minus 7 in neutral solutions. Obviously, when the solution is acidic, H plus is going to be more, so the concentration is going to be greater than 10 to the power minus 7 in this situation, and here it is going to be less than 10 to the power minus 7. So these are the values in terms of concentration. Now, if you really look at the values of pKw, this is another, pKw, anything that we are writing with a P, which is the strength of the particular value, we actually take a minus log of the value. Now, why we take logarithms? Because all of these values are generally exponential in terms. So you'll realize that when we write pKw, pKw is nothing but minus log of kW, and the value, this value turns out to be 14. This minus 14 and minus sign cancels out, and therefore looking at the pKw value is something that is very easy way to look at pH and pOH values. Now incorporating the same pKw value, we end up getting minus log of kW is equal to minus log of this, and therefore pKw is equal to pH plus pOH. We'll see what pH and pOH shortly is, but just remember this equation for the time being is pKw turns out to be pH plus pOH, and their value is equal to 14 at 25 degrees Celsius. Now, so a quick revision. Dilute acids has lots of water and therefore a small amount of acid, whereas concentrated acids have lots of acid and not much of water, so therefore they need to be handled carefully. Strong acid releases lots of H plus, and weak acids releases few of H plus. Now, the extent to which this H plus is given out by an acid, or for that matter OH minus given out by a base, is represented through a pH scale. So pH scale is one scale through which we can understand what are the values of H plus and OH minus given out. Now the strengths of acids and bases definitely is because of its H plus and OH minus ions. We have also seen how we can look through the equilibrium constant of acids K and Kb values. But at the same time, it can also be looked through multiple other ways, which, for example, is a universal indicator is one way to look at it. The P in pH is comes from the word Potenz in German or in Deutsch, which basically means power. So the scale measures the value of H plus ions from 0 to 14, 0 being very acidic and 14 being very alkaline, 7 of course being very neutral. And there is also a paper through which different colors can be seen and different pH values can be recognized. I've given few examples of strong acids and strong bases. For example, you have HCl, H2SO4, HNO3 as strong ones. Weak ones are CS3COH or carbonic acid. Similarly, a weak base sometimes is very difficult to remember, which is NH4OH. All of these values I've also represented here in terms of colors. So you can find that on a universal indicator, which is nothing but a complex of dyes. So there are a lot of multiple dyes put together. You'll find that the value actually goes from it's like Vibgyor. So violet is here, or the bluish are here, and the red ones are here. So acids are the ones which turn towards red, whereas bases or alkalis are the ones which turn towards blue. Just a quick note here: what is the difference between a base and an alkali? Base is anything that accepts. I mean, all the three definitions of Lewis, Bronsted, and ARRHENIUS can be used for a base. But alkalis are only the soluble hydroxides of first group metals, first group and second group metals. So alkali are special bases which are soluble and which tend to give out OH minus. So soluble bases are alkalis. Now this is the color array for litmus, universal litmus, or a universal indicator. And whenever you have a pH, a particular color is reflected in the solution, which can tell you what is the pH of the solution. And they change color depending on whether they're acids and bases as well. A quick look at some of the the pH scales that are commonly used. So for example, the hydrochloric acid that we generally use in the labs is about 0.1 molar, which is a very, very strong HCl. You can realize that it is so close to 0 that it's going to be a very strong acid. Whereas if you really take the spring water, which is the water that you drink, or most ideal water, even lemon juice or vinegar, you'll find that their acidity is very close to 2. So 2 also is quite acidic, and in fact, that's where vinegar, if you also taste it, it's pretty sour in taste. Even lemons are pretty sour in taste because of very high acidities. The wines that generally are used are generally around 3, whereas acid rains is somewhere around 4.6. NCRT actually mentions it to be around 5.8, but somewhere around 5 is where acid rains happen. The cheese, in fact, what we eat is also acidic in nature, and about 5 is its acidity. In distilled water, generally 7. Milk is acidic again. And if you look at the bases, seawater is alkaline in nature. Because obviously a lot of basic substances like calcium hydroxide, etc., are pretty much prevalent in seawater. Sodium bicarbonate or alkaline soils generally have a pH of 9. And a very, very basic solution is the oven cleaners. Basically, whatever we use in our even in our restrooms or bathrooms, whatever is used as cleansing materials, they are very, very alkaline. Even lime water is as alkaline as 12. Household ammonia, which is ammonium water, is alkaline as 11. So this is a quick look at the pH scale. Now, how do we identify acids and bases? Whenever pH is from 0 to 7, it's definitely acids. Lower the pH implies stronger the acid. Whenever pH is between 7 to 14, these are bases. And higher the pH value, stronger the base. So that's a quick look. Now here's a problem that I have mentioned for you. Really how to find a solution. So we have seen. We'll just get into a problem shortly. So because Kw is 10 to the power minus 14, taking logs, we can also write Kw as 14 and pH plus pOH, which we have just seen. Remember this, and therefore H plus ion is nothing but 10 to the power minus pH, or OH minus concentration is 10 to the power minus OH concentration. Similarly, pH is minus log of H plus, and pOH is minus log of OH minus, and Kw. So this is a quick summary of all the equations that are possible, for the pH calculations. Now let's look at a problem. I'm going to give you 1 minute. So Pranav is asking, why isn't spring water sour, sir? Pranav, actually, the spring water that we generally drink, is not really the true spring water. The ideal spring water should be the ones that are there in Himalayan waters. Having said that, I'm not sure the taste, because it's a very subjective matter on the taste, but you'll find that this is the acid spring water that they are mentioning. Okay, so these are spring waters which are basically found in, I don't know if you have seen Yellowstone national parks and all of those. So there is very warm water that is found, and they are called as acid spring waters. So not the spring water that we are talking about, that we drink, for example, the Himalayan water, etc., that they speak about these days. Yes, Rishikesh, we'll also be doing metals revision in some time. I'm just quickly coming to the end of acid bases. Here's a quick problem. I'm barely going to give you a quick 30-second time for this. So there is an ammonium solution and has an hydroxide ion concentration of so much. What is the pH of this solution? If you can quickly do in this next 30 seconds, I'll be very happy to look at this. I've also mentioned a hint there that how can you calculate pOH first. Okay, so by this time, I guess all of you must have at least got an idea of this. So what we do is we firstly find the pOH, because we have the hydroxide ion concentration. So we simply take the minus log of whatever hydroxide ion concentration is given to us. That value comes out to be 2.72. Now what we'll do is we will find the pH by subtraction from 14, which turns out to be 11.28. The other way is that you simply find the Kw, which is 10 to the power minus 14, and you simply divide the OH minus concentration. So you'll get the H plus ion concentration, and then you can find the pH, which will also come out to be the same value. So that's a quick way to really look at the, to understand how pH and pOHs can be found out. Now, this is one of the most trickiest chapters that most of you have been facing problem on. How do we really find the concentrations and express these concentrations of solutions? So the definitions that are very important for all of us, I've mentioned on one single slide here. So you'll find that molarity is nothing but moles per liter. Sometimes it is also expressed in millimoles per ml. Both of their values should be the same. Please note, whether you write moles per liter or millimoles per ml, the values do not differ. So 2 moles per liter is also equal to 2 millimoles per ml, because you're dividing the numerator and denominator both by 1000. The next very important definition for you is normality is equal to equivalence by liter or milliequivalence by milliliter. I'm going to quickly talk about equivalent weight here itself. So equivalent weight or equivalence is nothing but it is the n factor into your moles. So equivalence is n into moles, where n is basically valency, or it is acidity or basicity of a substance. So all of that, right? So if you have H2SO4, for example, the basicity of H2SO4 is twice, so n factor is 2. If you are looking at Ca2+, then n factor for Ca2+, because the valence is 2, n factor is 2. So equivalence is equal to n factor into moles. And the other way is equivalent weight. Equivalent weight is on the other side, molecular weight divided by the n factor. So please note, when we are talking about the weights, it is division, and when we are talking about equivalence, then it is multiplication. So when normality is spoken in terms of equivalence or equivalents, and therefore you can accordingly also find out that normality is equal to n factor into molarity, because it is moles and equivalents. So I'm simply dividing by liters on both the sides, and I end up getting this reaction, which is normality is equal to n factor into molarity. Again, I suggest that if any of this is unclear to you, please feel free to pause, go back, or after the class you can actually rewind this, come to this time, which is about 53 odd minutes, and have a view look at this. The next is formality, which is identical to molarity, not very different. And then the last one, which is most important, is molality, which is moles of solute divided by moles of solvent. This is the only way where the solvent comes in play. Okay, so solvent is prevalent only in the definition of molality, nowhere else. So remember this definition: it is the moles of solute divided by moles of solvent. In all other situations, it is always solution. It is the liters of solution, so on and so forth. It is only in molality that it is the grams or weight of the solvent. So a quick example, molarity, we have dissolved 12.6 grams of NaCl in water, making 344 ml of solution. Now they have asked us to calculate the molar concentration. So all that we'll do is we'll find out the moles of NaCl and we'll divide it by the volume of the solution. So what is the moles of NaCl? This is molarity. So moles of NaCl is 12.6 grams, but 1 mole of NaCl is 54.44 grams. And here we need to find about for 1000 liters. So 1 liter is 1000 ml. So I'm simply multiplying 1 liter divided by 1000 ml and 1 mole divided by 58.44. If you really solve this, you end up getting 0.627 molar NaCl solution. So this is a quick way to find out molarity when your weight and the volume of solution is given. Again, I suggest you can always pause this. The good part of YouTube is you can always get back to wherever you require a review on. Second problem is how many moles of NaCl are contained in 250 ml of a solution of molarity. So in this situation, molarity is given to us and we have been asked moles of NaCl. So you realize that molarity is moles per volume, moles divided by volume. Therefore, if it is 125 moles of NaCl in 1 liter, then in 250 ml, so much is in 120. In 250 ml, we will have 0.25 liters of solution, right? So in 250 ml, I simply end up for multiplying 0.25 into 1.25, and so many moles is what I require. So liter cancels out. I end up getting 0.313 moles of NaCl that are present in 250 ml of solution. Right. So you can again look back at this. I'm going to move slightly forward because we need to cover metals as well today. Another quick way to find out molarity: when weight and molarity is given, the volume is to be found out. How much volume is to be diluted it with. So molarity is moles per liter. You will find that when it is 0.75 moles per 1 liter, you will find that 15 grams of NaCl, this is 1 mole. So this is so many moles of NaCl in 15 grams. Now, if I need to have this much of molality, 0.257 needs to get converted to 0.75 per at a liter concentration. So I simply multiply those and I end up getting 0.34 liters of solution has to be taken to dissolve 15 grams of NaCl to get that amount of molarity. Right. So moles of solute divided by concentration gives volume of solution. This is another quick digest for you, or a quick revision for you. These are some formulas that are also used in your problems. So weight by weight is mass of solute divided by mass of solution into 100. Weight by volume is mass of solute divided by volume of solution into 100. And volume by solute divided by volume of solution into 100. So that's a quick way. Always note that gram per ml and kg per liter, these values will always be the same. So whether you write gram per ml or kg per liter, both of them will remain the same. Right. There are a few problems. What is the concentration in percent weight by volume of a solution containing so many grams of potassium nitrate in 177 ml of solution? You'll realize that we can find weight by volume as mass by volume. You can always pause this and have a relook at all of these questions so that you can have a practice. I'm getting this, just so that you have these questions with you and the solutions also with you. The intent of this PPT is to give you some questions that you can also revise. So after the class or whenever you find time, please pause this, have a relook, and you can have your own practices. So while we are doing weight by volume, we simply take the mass divided by the volume in which it was dissolved, and we write it as percentages. So in a liquid solution, you will take volume by volume. So simply take the volume that was dissolved of solute that was dissolved in the volume of solution. So in this scenario, you'll write 3.2 divided by 6.5 into 100, and you'll end up getting 49% volume by volume. What happens when you are taking weight by volume? So 5.7 grams of solute is now, and we need to find what was the volume of the solution. So in weight by volume, it is 1.85 grams divided by 100 ml. Now we know that gram per solute, and or you can also see that gram solute per ml solution is what is weight by volume. Now we want to get ml of the solution. So you simply flip these values. You'll find that 5.7 gram of solute into 100 ml by solution divided by gram per solute, the gram per solute will cancel out, and you will find that 310 ml of solution is what you need to dissolve 5.7 grams to get 1.85% weight by volume solution. So the solute in grams divided by concentration will give you the volume of the solution. So these are quick shortcut formulas that you can also keep. So this brings us to the end of acids and bases. And I'll be happy to hear from you if there is anything that you want me to really say on acids and bases. I'm going to jump to the metals revision because I can also give you some input on the metal revisions, and so that you have all of this data with you. And you are most welcome to ask up your queries. I'll be available on WhatsApp even after this class, so feel free to do that. Let's understand the metals chapter now. Yeah. So metals chapter actually deals with three major portions. The first is to understand what are metals, non-metals. Second is the entire metallurgy, the extraction process. And third is some important compounds and their reactions. So metal chapter is basically in the autonomous syllabus is three broad sections or spectrums of it. So firstly, let's understand metals and how are they related to the metallurgy or the extraction process. So these are some important terminology of extraction or metallurgy. The first one is minerals. So what are minerals? Minerals are those ores. So minerals are all of those substances which are found in the Earth's crust with the particular metal that we are looking for. So minerals are simply substances with the metal in it. Now, from the minerals, whatever we can use to profitably take metal out are ores. So if you have to draw the Venn diagram, as we have done it with BRONSTED, LOWRY, and ARRHENIUS. So this is the ores. So ores is a very small part of minerals. So these are all minerals. Not all minerals can be used as ores because ores need a very profitable extraction, and therefore they both are not the same. Now, what is ganch, or they are the undesirable materials that are present in the ore, basically impurities, or all that we do not want in the ore to be there, so that we get our pure metal. And what's metallurgy? Metallurgy is the science or the processes, the scientific and technological processes that are used to extract metals or to isolate metals from its ores. So remember these four definitions as a quick look at the progress of metallurgy. Now, this is one slide where I have given you all your important metals. In your syllabus, you have the following definitely. You have your sodium, you have aluminium, potassium, magnesium, you have calcium, you have zinc, and you have iron. So all of these seven are pretty important for you. I've just mentioned their most important ores. Please remember, ores generally are of three types. The most common ores are actually carbonates, okay, because they are the most stable and very unreactive. The second type of ores are sulfates. Okay, there are sulfates and sulfides. Generally are considered in the same domain. So sulfate, sulfide ores. And then you have basically either your halides, oxides, okay, halides, oxides, or some other like pyrites, which are basically a mixture of any of those two, halides and sulfides, or any of those two. For example, you'll see this is a carbonate, a bicarbonate ore of sodium. You'll find that this is an halide ore. You'll also see that this is an oxide ore of copper. In zinc, this is an oxide ore. So all of these ores are pretty much seen. Then you'll realize in iron, you'll have again lots of oxides ores and carbonate ore. So all of these are examples of different types of ores that are possible. Okay, so going forward, these are what are the steps of metallurgy that are necessary for extraction of metal? The four steps are, the first is you have to concentrate the ore. Basically, as ore just gets in, you have to do some basic preliminary methods which can get a higher concentration of the ore that we want to process. The second is conversion of this concentrated ore to oxide. What we do is we try and convert these ores to its oxygen compounds. And because oxygen compounds are the easiest to get reduced, and they are also very easy to manage and handle, also very profitable. Secondly, the third thing that we do is we reduce these oxides to metals. And lastly, we refine these metals. Now we'll look at all of these steps of in elaboration of all of those. So what is concentration? It's basically to remove sand, clay, rocks, which are the most primary impurities, where you don't even need a process. You simply can break it down into smaller parts, and you end up getting a concentrated ore. It's sometimes also called as dressing, ore dressing, or benefaction. Now there might be several steps based on, most of them are generally physical, but depending on the property of the metal, you can actually look at what can you really use as physical processes. Okay. So there is a quick question on what is the point of having two sedimentation. I'm going to come there in some time. Okay. Now let's go back to our concentration of ore. The type of metal, its available facilities and environmental factors are taken in consideration whenever we are doing the concentration process. So these are two important points that you should remember in concentration of ores. The next is what are the different ways of concentration. The first one is gravity separation. It is also called as hydraulic washing. So hydraulic washing is basically when you are putting all the ore and simply under a huge pressure of water, you are trying to wash it off. So what happens, because of the gravity, the denser or particles which are heavier, they are not washed up that easily, but small particles like sand and ganj particles are actually washed away pretty easily. Heavy ores are left behind. So that's the hydraulic process. Very simple. You can draw diagrams for it. Your textbook mentions a diagram. You can please use that. But there's nothing technically really dense or critical about it. The next is magnetic separation. So basically we use the property of being having magnetic properties or non-magnetic properties between two components to separate them. So you have a magnetic separator here. So how it works is that the magnetic separator can actually keep on throwing off non-magnetic substances here, but the magnetic substances will fall just below a huge magnet that is present. So this is an electromagnet that we use, and the electromagnet makes all of these substances fall close to the magnet, and the others are thrown out. So some of the ores that actually use this process is magnetite, chromite, pyrolusite, even cassiterite. These are some of the ores where you can use the magnetic separation as a process. Now that all of these processes concentrate ores. The next process is froth flotation. One of the most important properties is selective wetting of a substance, which means that how can you really get water connected to, or let's say dissolving certain amount of substances and the others not. So for example, sulfides are very easily bonded with or dissolved or soluble in pine oil. So you put all the sulfide ores in pine oil, I'm sorry, and you actually put in a lot of froth in it, by presence of a lot of air. So what happens is that the froth really accumulates over the solution, and then it can be taken out, and the ganj particles remain in the solution below. Now there are some froth stabilizers also you use. Basically cresols and aniline are froth stabilizers. So basically if two sulfide ores are present, then it's possible to separate those sulfide ores by using these stabilizers. So by adjusting the proportion of oil and water, and by adding some depressants. So these are the additional compounds that you can use to selectively between two sulfide ores also make things work out. So one of the things that you have as an example of ore is your ZNS and PBS. So the depressant is NaCN here. So NaCN basically is used in terms of used to separate ZNS and ppb. So both of that is possible, and that's one of the ways to use a depressant as mentioned to you. Okay, so that's froth flotation method, one of the ways to make the sulfide ore separate from its solution. And the last one is chemical separation, or also called as leaching, especially used in bauxite. It's also called as Bayer's process. Now, what basically happens in this is whenever the ore is treated with a soluble solvent, the solvent dissolves the ore, but not the impurities. Okay. So, for example, Al2O3, which is present in bauxite, we use NaOH, and this NaOH is one that actually dissolves Al2O3 to give sodium aluminum hydroxide. Now, sodium aluminum hydroxide is basically, it can further be also reduced to give Al2O3 back with water, that is water of crystallization, and sodium bicarbonate. So you'll realize that you firstly dissolve Al2O3 to give sodium aluminum hydroxide, and then further you're reducing sodium aluminum hydroxide to give back Al2O3. So this is the process of leaching, where through a cyclic process you have achieved your ore and its concentration one more time. So yeah, so that's a quick look at leaching. Now let's look at the processes of conversion of ore into oxide. Major processes are two, and they are called as roasting and calcination. In roasting, you will find that there is a lot of supply of air, and therefore oxygen is involved. And in calcination, you will find that there is no or limited supply of air. Therefore, there is no oxygen involved. Calcination mostly takes place with carbonate ores. Please note that, with carbonate ores. And roasting takes place with sulfide ores. Okay, because carbonate ores end up giving CO2 just on heating, and therefore there is no air required. But sulfide ores end up giving SO2 on heating, and therefore there is oxygen required. So S gives SO2. So roasting is with sulfides, most suitable for sulfides, and calcination is most suitable for carbonate ores into oxides. Now, once the oxide is formed, how do you really get it to metals? So the process of converting metal oxides into metals is called as reduction, and it needs special reducing agents. Most of the times it is done by carbon, and because it is done by carbon, it is called as smelting. So smelting is that process which uses carbon to take out the oxygen from the metal oxide to give you CO2 plus metal back. So that carbon is a very strong reducing agent and very commonly used as well. Carbon monoxide is also used in most of the scenarios. We are going to look at some extraction processes, for example, extraction process of aluminium and magnesium, aluminium and zinc for that matter. And we'll find that carbon and carbon monoxide are very well used in both of these processes. Now, a very common question is why? Oh, yeah. Thanks, Rishikesh, for that. Maybe probably a small error in typo there. Right. Now, one of the so once we have received the iron, so why do we need iron to be extracted in blast furnace? Now we are looking at the extraction process of iron, and we all know that it requires a blast furnace to be used. So what we really do with the blast furnace? So one of the reasons that we use blast furnace is because it can be easily displaced by carbon. And the method also is very economical, because if you try to displace iron through an electrolytic method, it is going to be much more costly. Okay, because you will have to use bare electricity, and expenses in that are pretty huge. So iron is used and extracted through a blast furnace just because the carbon can easily displace iron from its oxide. Now let's look at how this reaction really happens. So this is the typical diagram of a blast furnace. I'm going to go to the next page and then come back, next slide and then come back. Essentially, what we do is we enable this extraction of iron from its ore through a mixture. This mixture is called as charge. Whenever iron ore like hematite is used, it often contains sand and iron oxides. Okay, so hematite is nothing but again an oxide ore of iron. So what do we do is we mix this hematite with limestone and coke, which is mainly carbon, and then we put this charge. This entire thing is called as a charge, and this charge is then put through a giant chimney which is called as a blast furnace. It's very tall, and yeah. So Pranav, that's right. It's just a jet of compressed air which agitates in froth flotation method. Right. So now this charge is what is put inside the blast furnace, which is generally about 30 meters high. And internally it is lined by fireproof bricks because it should not damage the external surface. And then the hot air is blasted through the bottom. So if you look at our diagram now, the charge, which is limestone plus coke plus hematite, is put through this blast furnace, the mouth of the blast furnace. And all the waste gases, there is an opening for the waste gases. Whatever iron is coming through this, it forms and it trickles down because at such a high temperature it actually melts. If you realize that the temperatures are very high at the bottom and very low at the top, so at this part itself, carbon and carbon monoxide and CO2, everything is formed, where you can see my cursor, and they are given out as waste gases. So most of the impurity is taken out at half of the height of the blast furnace itself, and the iron that comes below is purified even more and liquefied, in fact, because of the hot blast of air that you are putting through. And only what remains at the bottom is a molten slag and molten iron. So molten iron is what is taken out through a plug hole. The slag being lighter than the iron, it floats over the iron, and there is another opening to take out the molten slag. The molten slag basically consists of your calcium carbonate, your whatever limestone which went through unreacted, and all the impurities. That is what slag is used for. Now coming back to, so this is a hematite, and this is how, so I've shown left how an hematite looks like, and I've seen on the right how the metal really comes out. So this is how really a iron comes out. Now, what are the reactions that really take place in this process? Some of the reactions I have outlined here is basically the oxygen and carbon. They form carbon dioxide directly. This carbon dioxide is, the limestone actually breaks down to give you calcium oxide and another carbon dioxide. Now, both carbon dioxide that are formed in the processes 1 and 2 in both of these reactions further end up giving us carbon monoxide. So our intent of forming carbon dioxides also is to, at the end of the day, to either get carbon or carbon monoxides, because they are the ones who reduce iron. These carbon and carbon monoxides end up reducing the hematite ore, that is Fe2O3, to give us liquid iron and CO2 gas. Now this CO2 gas, you can imagine that again CO2 which comes in here is further useful again in this first three processes to give more of CaO and more of CO. Now whatever CaO was formed, we basically add some amount of silica, which is SiO or SiO2, and you'll find that the calcium comes out as calcium silicate. This should be SiO2. There is a 2 missing here. So an SiO2 with CaO ends up giving CaSiO3. That is calcium silicate, and calcium silicate is what is the slag that we have we saw in the figure. Now both slag and iron are drained at the bottom. Of course, slag being lighter is taken out through the upper chamber, and iron being heavier is taken out through the bottom chamber. Now just a quick note for all of you who are still listening is that this is a very simplistic model, because I find that most of the students complicate writing answers and they forget a lot of reactions. So I've given you a very simple model of how you can really do extraction of all the three metals: aluminium, zinc, and iron that we'll see now. So in iron, this slag is used to build roads, and iron, which is molten, is poured into molds and left to solidify. That's how you end up getting cast iron, and railings or storage tanks are made out of it. The rest of the iron is simply used to make steel. Now what are the different types of ions? Of course, you have pig iron. So the iron which is directly obtained from the blast furnace is called as pig iron, and it is a very impure form of iron. It contains almost 4% of carbon. Also impurities like sulfur, phosphorus, silicon, manganese are all present in there. From there we actually end up getting cast iron, which is basically simply you melt pig iron and with some more iron in it, and use coke again. So what happens is all the impurities are reduced further, and it contains about only 3% of carbon now. It is very hard and brittle because of the presence of carbon. And the last one is wrought iron. This is the purest form and used for commercial irons. It is also very malleable. So what happens is whatever carbon is remaining in cast iron, basically you do what is called as oxidative refining of pig iron in another furnace, where all the carbon is taken out as carbon monoxide, and that's how you end up getting. So I've just written a reaction here in in terms of Fe2O3 and carbon. So you'll find that we'll end up getting carbon monoxide and a pure form of iron. So this is sometimes also, this slag is also called as flux. So limestone is slag with which is of limestone is also sometimes named as flux. So these are the same reactions from the previous. I've just kept it here so that you can relate to formation of wrought iron and cast irons per se. Now, yeah, so now let's look at the extraction of aluminium from bauxite. This is the second extraction that you have for your syllabus coming up. Now, what are the raw materials? Of course, you need to use bauxite, which is Al2O3, which generally has a melting point of 2000 degrees Celsius. Also, you use cryolite, which is sodium aluminium fluoride, which is Na3Al(F6). Again, it is generally used at a lower boiling point, which is about 900 degrees Celsius. And then you have to use carbon electrodes. So all of these three are the raw materials that you basically procure. Now, let's look at the process. So basically, cryolite is added, below its melting point, and it basically dissolves the ore and bauxite, to give aluminium oxides. And bauxite ore is continuously added to this mixture. When potential difference is applied to this mixture, you will find that Al3 plus starts getting attracted towards the negative electrode, whereas O2 minus gets attracted to the positive electrode. So the function of cryolite is just to dissolve the ore, and the ore is continuously being added so that the process remains happening. At cathode, as we had mentioned, Al3 plus gains 3 electrons, so it undergoes reduction to give liquid aluminium. This aluminium sometimes is also deposited on the electrodes. At anode, oxygen loses its electrons and a lot of oxygen is formed. These oxygen actually attacks the carbon anode, and a lot of carbon monoxide and carbon dioxide is also formed, and therefore carbon anode keeps on dissolving and it needs to be replaced. This is one of the problems of extraction of aluminium through this cryolite process. The Hall-Sarod process diagram is, I've just mentioned here, in a short. So you can write this Al2O3 in molten cryolite, and the carbon electrodes have been mentioned. Please note that the carbon electrodes are of different sizes. There are more electrodes that I've used at one end and very less at the other end. The one that is singly used is basically the carbon electrode that is cathode. Why? Because at cathode, aluminium gets deposited, and a lot of at anode, you'll find that there is a lot of oxidation that is happening, and these electrodes need to be changed from time and again. So therefore, more electrodes need to be used at anode, and a single electrode at cathode suffices. And as the temperature still is high at the bottom, all the aluminium that gets deposited on the carbon electrode is taken at the bottom and taken out in the molten form. So a very simple, short way of representing aluminium extraction is what I wanted to show you through this diagram. And there is a quick usage or method that you can also say through anodizing. Anodizing is one of these processes. So this is a form of electroplating using oxygen, and commonly used for aluminium. So basically, when aluminium is exposed to air, it forms a thin protective layer of aluminium oxide. And for better production, we use a thick layer of this thing. So you see, aluminium, the good part about aluminium oxide is once it has formed the oxide, it does not make any more aluminium react with oxygen that is covered internally. So if I have to draw a figure for this, maybe just to show you. So if aluminium oxide layer is formed at the top corner, which is Al2O3, you will find that the lower aluminium remains protected. So anodizing is a very good method to protect any metal. So the metal remains below, and Al2O3 is at the top. So this anodizing actually can help protect metals that are at the bottom or covered at the bottom. So that's a quick look at anodizing. Some more few points. The aluminium anode, is made as the anode in a sulfuric bath, and then oxygen is also produced at the anode that combines with aluminium to form this porous layer of aluminium oxide, which is almost 1,000 times thicker compared when exposed to air. Now pores can be sealed by dipping into hot water and colored by using dyes which can be absorbed into. So this is another way of anodizing. Just a quick note for you, just for your understanding, but not really connected, just as a use of aluminium. Now, some more uses of aluminium to make electric cables. They are very low in density, very good conductors. Therefore, they are used, to conduct electricity. But they are also very resistant to corrosion, so very good to make wires. They definitely are used as full conductors because they are non-toxic, and they also are very resistant to corrosion. So can be they're conductors of heat as well. So used to make containers, utensils, aircraft body, rocket bodies, or for long travels where fuel efficiency is very important. Low density light aluminum comes very handy at these positions. Now the next is zinc extraction in our syllabus. Let's look at how zinc is extracted. Some of the most common elements of zinc are sparrelite and zincite. uh, I'm going to tell you these processes in very short, just so that you can remember them, because I know most of you generally simply memorize from the text. So to give you a outline of these processes, I have mentioned that there are 6 basic steps of zinc extraction. The first one is you treat the ore to get concentrated rich zinc. The second is you roast this zinc to convert zinc into a soluble form. Then this roasted concentrate, which is basically zinc oxide, is used to form zinc sulfate. And then zinc sulfate solution is purified further by precipitation of impurities. Finally, zinc is removed from the zinc sulfate solution by electrolysis, and then the molten zinc is converted into zinc sheets as ingots. Okay, so that's the method. As your textbook mentions, low grades of ores are needed for concentration. ZNS generally melts at 1500 degrees Celsius, and we reduce ZNO, which is then distilled off and cooled further. So how does this everything happens? The three reactions that are most important in this is ZNS with oxygen gives zinc oxide and SO2. Similarly, zinc oxide with carbon monoxide gives zinc, which is where the zinc is converted to zinc oxide is converted to zinc metal, and carbon with carbon dioxide is given as CO. So the steps, if you really see, in your retort, vertical retort that is mentioned, that's the the setup that we use for zinc extraction, is that there is a grinding flotation, which is the concentration method. So rock, lead, and copper concentrates are generally taken out at grinding flotation, and then you end up getting zinc concentrate. This zinc concentrate is then roasted. So when roasting, SO2 comes out, and you get zinc calcine. Then the process called as sintering happens, where another lead, cadmium, and SO2 impurities are taken out. You end up getting zinc oxide agglomerate. That is where coke is introduced, like any other. You end up getting ZnO powder and zinc vapors. The zinc vapors are condensed. This condensation gives liquid zinc, and then finally you do vacuum distillation or fractional distillation to end up getting pure zinc. Because zinc has a very low melting point, it can simply be evaporated and condensed further. So this is a quick look at zinc extraction. uh, Zinc extraction is generally comes for about 3 marks or 4 marks if all the processes are asked with the diagrams, maybe even 5 marks. So you can have a look at this. Now quick look at the properties of metals and non-metals. Of course, this is the easiest part of the entire metal chapter. We look at 8 different properties between metals and non-metals. There's physical states. Mostly all the metals are in solid state, all the non-metals are in gaseous form. The boiling point, melting point of metals are very high, except that for gallium and cesium. Similarly, for non-metals, they have a very low melting and boiling point, except for diamond and graphite. Then the densities is very high for metals, non-metals being very low. Malleability and ductility are also very high for metals, and very low for non-metals again. Metals are very conductive, and they conduct both heat and electricity. Non-metals only conduct in graphite. All other non-metals are very poor conductors or bad conductors. Lustre is basically the shine that we have. So you'll find that metals possess this lustre, whereas non-metals do not possess, except for iodine, which is in solid state. Then you also have sonority, which is the property of having a reverberating sound when it is struck. Metals show this sonority, non-metals do not. and the hardness of metals is more than non-metals. Some quick reactions that are important of metals and non-metals. So with oxygen or with air, all the metals end up forming its oxides, and similarly with non-metals, they end up forming its oxides. We'll also realize that all the oxides basically we are seeing were basic in nature, but for zinc and aluminum they are amphoteric, as I had already mentioned. For non-metals, all of them generally either are neutral or they are basically acidic in nature. Then the reaction with water is important for metals. So in water, you'll find that it ends up forming hydroxides and hydrogen gas is given out. Whereas non-metals do not react with water. They or even with steam, okay. But non-metals, because the reason is because they cannot give electrons to hydrogen water, and therefore no hydrogen gas is released. So there is no reaction of non-metals with water. Metals do react with water to form metal hydroxides. With dilute acid, all the metals end up giving salt plus hydrogen gas again. So very similar to reaction with water. With dilute acids, all of these metals end up giving hydrogen gas, whereas with non-metals, in non-metals also end up giving hydrogen gas with non-metals actually do not react with acids, and they do not end up giving hydrogen gas. And the reason is because they actually do not have any hydrogens to give. So very similar to water, as non-metals do not react with water, similarly they do not react with hydrogen gas as well. I've simply mentioned an example here of Mn, but this is actually an example of a metal reacting with a dilute gas to give out hydrogen. So remember that this is an example of the metal. Okay, so probably it's just shifted to the non-metal section. Now, what are the reactions with salt solutions? So depending on the reactivity series, we know that there are reactive metals and unreactive metals. So because based on the reactivity series, zinc being more reactive will displace copper out of this, and zinc sulfate is formed. So whomsoever is the reactive will remain in the solution, and the unreactive ones are precipitated out. Similarly, here chlorine is more reactive, so bromine is basically precipitated out, and NaCl is formed. So the same principle applies to both metals and non-metals. The reactive ones precipitate out the unreactive one. The fifth one is the chlorine, reactions with chlorine. So all the metals form chlorides, and all the non-metals also do form chlorides. Non-metals generally would be hydrogen. For example, bromine and iodine, etc., do not react with chlorine, but non-metals like H2 do. I mean, H2 is technically, you'll find that it is considered as metallic and non-metallic both, because it contains both the properties. So, but yes, other non-metals like phosphorus also ends up forming PCl3. So non-metal chloride definitely is formed. Now the reaction with hydrogen, metals form hydrides, whereas non-metals also do form their hydrides, except that in metal, hydrides are H minus, and here it is actually a hydrogen ion. So it is a hydronium or hydrogen ion, which is H plus. So in non-metals, you'll end up getting H minus, whereas in metals, you end up getting H minus, and non-metals, you end up getting H plus. Yeah. Now, some of the important compounds that are there for our studies. This is the last part of the metal non-metal chapter, and probably then after that we'll pause if you have any questions. So one is that the preparation of sodium hydroxide. The process is called as chlor-alkali process. So for example, you basically take NaCl. I'm sorry. Yeah, so basically take NaCl, NaCl water, which is the brine solution, and you electrolyze it. So as the NaCl solution electrolyzes, a lot of NaOH is formed, giving out chlorine gas and hydrogen gas, at different terminals. It is one of the most used base. This process is called as chlor-alkali because we end up getting chlorine also, and we end up getting alkali as well. So because chlorine and alkali are produced, it's called as the chlor-alkali process. It is one of the most used base, and used in multiple industrial processes as basic hydrolysis of polymerization, etc. The next most important substance for us is the bleaching powder. It is nothing but CaOH twice plus Cl2, giving CaOCl2, which is calcium hydroxide and chlorine put together. This bleaching powder is used as a disinfectant as well as as a purification reagent for a lot of processes, especially in textiles and laundry. Okay. Now in your text, they have mentioned a few more examples. I would recommend that you also have a look at those. Let's look at baking soda. Baking soda, most commonly known, it is nothing but sodium hydroxide. The process through which it is produced is called as the Solvay process. It is the same process that is also used in making washing soda, which is Na2CO3. So essentially, sodium chloride in water ends up giving, with ammonia and carbon dioxide ends up giving ammonium chloride and sodium hydrogen carbonate. The process produces. So on heating, so here are the steps. So we use NaCl plus ammonium carbonate, actually. Okay, NaHCO3. This is NaHCO3 to begin with. This actually ends up giving us NaHCO3 plus NH4Cl. So this, but since NaHCO3 is very NH4CO3 is very unstable, we use that as ammonia plus CO2 plus water. So all of this is put together to form NH4 or NH ammonium bicarbonate, basically NH4HCO3 plus NaCl. So they simply exchange their cations anions, and you end up getting NaHCO3 plus NH4Cl. So that is the reaction that happens. Now this the baking soda that is sodium bicarbonate, if you simply heat it up, you'll end up getting sodium carbonate plus CO2 and water. Now, what are the uses? Of course, it is used to bake. It is used to make things fluffy because the effervescence that comes out of the CO2 is pretty useful in making, in baking purposes, as well as making contents crispy and fluffy. The next is washing soda. We've already seen how it is prepared. The same Na2CO3, NaHCO3. When you heat, it ends up giving Na2CO3. When washing soda is put in water, you actually end up getting a crystalline substance, which is Na2CO3 10H2O. It's used in glass. It's used in soap and paper industry. It's also used for a lot of domestic purposes, used to remove the hardness of water or manufacture of borax as well. And then we have gypsum and plaster of Paris. So let's understand what is water of crystallization. It is basically the fixed number of water molecules present in one formula unit of a salt. So if you heat copper sulfate crystals, water droplets appear, which means that copper sulfate crystals had some water inside it before we started heating it. So gypsum is basically with that water of crystallization. Its formula is CaSO4 twice of H2O. When you simply heat gypsum, some water is lost, and you end up getting plaster of Paris, which is CaSO4 and half H2O. Okay, so this is formed after heating this gypsum further, and this plaster of Paris is used at multiple places. For example, it is used in to plaster the fractured bones. If you simply add small amount of water to it, you will find that it again gets back to gypsum, also hardens up. So these are some of the uses are making toys, decorative material, and smooth surfaces. So those are the uses of metal and compounds. We've just seen all of these parts, and I had a query coming in from one of you, and let me just look at the query. I'm not sure if you are still there. Yeah, so it said that in the yeah, so this is the sedimentation process, and the question is, in the sedimentation process, why have we used 2 cylinders instead of 1? Now the reason for this is the reason for this is so no, that's from a different query. Okay, cool. Now I'm just going to pause here, and if there are any further questions, I would like to hear from you guys. If you feel that there's something that you have to share, I'll be more than happy. I'm available on the WhatsApp. I see that only a few of you are still present. If you are still there, Happy to see you. But if you've already left, that's also fine. I request that all of you look at the the presentation one more time, and if there is any queries, I would be most happy to really answer them. You can reach out to me on WhatsApp or any of these media. Thank you so much. Nice having this session with you, and I look forward to interacting with you in the coming coming sessions. Thanks so much. Thanks so much once again.